So up until now, we've sketched sine, cosine, tangent, and cotangent. All that's left to talk about is what do the graphs of secant and cosecant look like. Again, we can do this point by point, making a table of values, but I think doing it logically might save us some time, and it'll allow us to understand why the shapes look the way they do. Well, as we did with the tangent function, we will start off by talking about the definition of secant and cosecant. Remember or recall that secant and cosecant, by definition, are the reciprocal functions of sine and cosine. Specifically, secant is defined as 1 over cosine, and cosecant is defined as 1 over sine. So just like with the tangent function, how tangent was defined as a rational function, so is secant and cosecant. So in terms of the shape, I don't even know what it looks like right now, but I expect it to be something crazy with vertical asymptote, because most rational functions will have vertical asymptotes. But this is very interesting. Yesterday, tangent was defined as sine over cosine, so it's dependent on two things. Today, since we're looking at pure reciprocal functions, secant and cosecant are only dependent on one other function, meaning these two quantities, depending on what I'm looking at, say secant and cosecant, they are inversely proportional to each other. Cosecant and sine are inversely proportional to each other. So in terms of figuring out what they look like, I know that whatever one function does, the other function does the exact opposite. So instead of going to Desmos, let's see if we can't figure out what these shapes should look like. So the first thing I'm going to do is I want to take a look at what do the basic sine and cosine function look like. So let's talk about the parent function, or let's ask this question. Let's start off with cosecant. What does y equals cosecant of beta look like? Well, since cosecant is related to sine, it's probably going to be related to what does sine look like. So let's go ahead and refresh our memories on what the sine of x looks like. So I'm just going to graph a generic xy axes, right? It's very long horizontal, so that's most trig graphs look like that. And I know we have 5 special x values, 1, 2, 3, 4, 5, and we know that sine is trapped between 1 and -1. And the pattern for sines is equilibrium, max, equilibrium, min, equilibrium. And at least for one period of sine, it has this wave-like pattern. So in the black is y equals sine of x. So in the gold here, I want to see what does y equals cosecant of x look like. And remember, cosecant is the reciprocal sign. Well, as discussed yesterday in previous units, for rational functions, you will have vertical asymptotes wherever the denominator equals 0. So I know for the cosecant graph, I'm going to have vertical asymptotes wherever sine equals 0. Well, in the black graph that we have here, y equals 0, or excuse me, sine equals 0, at x equals 0, at x equals, I didn't label the x-axis, but this is pi halves, and at x equals 2 pi, right? So even if I didn't know what those x values were, visually, those guys are the x-intercepts of sine, so I know that they will have vertical asymptotes there. Now, without being very, very specific, it's hard to find reciprocals. So for example, like, I have no idea what this y value is, so I can't reciprocate. But there are two other easy-to-read y values, this point and this point here. Right. Let's start with this point. I know he has a y value of 1. That's what this says here. So for the cosecant graph, I know you just have to reciprocate 1. Well, it turns out if you have the number 1 and you take the reciprocal of it, it's still 1. So I may not know what the whole graph looks like, but I know they share the maximum and the minimum. Now, to figure out the rest of the graph, we have to remember one important idea. Cosecant and sine are inversely proportional to each other. So whatever the sine graph does, the cosecant graph should do the exact opposite. So let's start at x equals 0 and then trace along the sine graph. Well, okay, as I go at x equals 0 and when I go to the rightwards, do we see here how the graph is going up to the number 1? Well, that tells me for the cosecant graph, he should do the exact opposite. Instead of going up to positive 1, instead the cosecant graph should go down to negative 1. Now, since this is a vertical asymptote, it wouldn't make sense to go down here because this is going up. So I know that for the cosecant graph, he needs to start up here and go down to that positive 1. Let's keep tracing. As I go rightwards, do you see how the sine function is decreasing? He's going downwards. Well, since cosecant needs to do the exact opposite, I know cosecant will go upwards. And we can rinse and repeat. Do you see here how the next segment of the sine function is going down to negative 1? So I know that the cosecant should do the exact opposite. Instead of going down, he's going to go up to negative 1. And then, of course, we can finish the picture off thusly. So what we see here is one cycle of the cosecant function. This is one period of the cosecant function. So what I expect you guys to graph on your own is the gold. You don't have to graph the black sine function, just graph the yellow cosecant function. Let's do the same exercise. Let's see what, actually, you know what? Just so you don't take my word for it, let's see in action in Desmos. Like you can see a nice, neater picture here. So here's the cosecant function. What does the cosecant function look like? It looks like a whole bunch of u's, parabolas here. And not surprisingly, that's indeed the case that we have here. And notice how, at least when we did it by hand, one important idea was that they share relative max and mins. They just flip-flop. Well, we can see that when I activate the sine graph. Right. I hope you guys can see that they only touch, they're tangent only at the peaks and troughs of the sine function. So that's pretty cool that we were able to see what this graph looks like just by using pure logic. Let's repeat the same exercise with cosine and secant. Now, we saw earlier in the week that, sine and cosine, they're basically the same shape. So it should make sense that this cosecant and secant should share the same shape. And spoiler alert, that is the case. So what does secant look like? So we'll do the same thing. We'll start with cosine. So I'm going to graph a generic cosine graph. Long horizontal, slight vertical. 5 special x values. 1, 2, 3, 4, 5. Has a max of 1, min of negative 1. And the pattern for cosine is max, equilibrium, min, equilibrium, max. So what I graphed here, not so great, but it's close enough, is cosine. So I want to see what secant of x, which is just the reciprocal of cosine, looks like. And as stated before, since cosine is in the denominator, wherever the cosine value equals 0 should be a vertical asymptote. So we have 2 places where cosine equals 0 in the standard picture. So those guys here should be vertical asymptotes. As stated before, when you reciprocate the number 1 or negative 1, you get itself. So these points here should be on the secant function. And as we said before, since secant is the reciprocal of cosine, its behavior should be the exact opposite of cosine. So let's start at x equals 0 and go rightwards. At x equals 0, we notice that the cosine is going down. So the secant function should do the exact opposite. It should be going up. Next, see how this next portion of the cosine is going down to negative 1. So the secant should do the exact opposite, going up to negative 1. And I think you guys get the idea by now. You guys can sort of understand the shape or see the pattern that this ends up being one period of the secant function. Now, yes, we did typically do a no-no. We split one of the parabolas, one of the U-shapes. We have one here and cut off here. Would it make a better picture if we continued on to the right or perhaps started in the negative region? It would make a nicer picture, but it would also introduce a different technique. And I want to make this as simple as possible for you. I don't want you to learn any new techniques. This only utilizes techniques of sines and cosines. So this right here would be an acceptable picture. This is what I would be looking for. What am I looking for 4 points? This half a branch, this whole branch, and then this half a branch. That's what I'll be looking for. So that's it. That's the big surprise. Oh, and by the way, if you wanted to see on Desmos, here you go. Here is secant and cosine. Not surprisingly, since sine and cosine share the same shape, secant and cosecant share the same shape. It only looks different because I'm only making you graph one period. If I were to make you graph all of it, multiple periods, they would look like the same picture. So that's it. In terms of new material, you just need to know the shapes. So again, here's cosecant, and here is secant. But in terms of actually sketching them, it is 100% the same as sketching sine or cosine. Because secant and cosecant are dependent on sine and cosine, you first run through the motions of doing sines and cosines before you go ahead and actually graph the secant and cosecant. Let's see this in action with a handful of examples. So suppose I ask you to sketch f of theta equals 2 secant of 1/2 theta minus pi fourths plus 1. Right? So it's a secant function. Oh no, this is scary. Here's the idea. The first thing I want you to do is think in terms of the reciprocal function. So because we have secant here, I want us to think of cosine. So everything in the process of sketching this guy in terms of finding the critical x values, what is the period, chopping up into the special bits, even this pattern, I want you to think of cosine. So let's go through the motions. By now, after doing 2 sets of these, we should be a little bit faster. So we know the equilibrium line is at y equals 1. We have a right of pi fourths. I know my new period, since I'm thinking of cosine, is 2 pi over 1/2, which is 4 pi. And then I have an amplitude of 2. Right? So this should just be a rehash of sine and cosine. So since my period is 4 pi, my interval will be 0, that new period, 4 pi. But we had a phase shift of right by pi fourths. So my new interval that contains one full picture will be pi fourths, what is that? 17 pi fourths. And just as before, we're going to make our XY table. 5 critical values, just as before. Pi fourths, 17 pi fourths. So we'll go ahead and make a whole bunch of averages. So right smack dab in the middle will be the average of pi fourths and 17 pi fourths, which is 9 pi fourths. Right here will be the average of pi fourths and 9 pi fourths, which is 5 pi fourths. And right here will be the averages of 9 pi fourths and 17 pi fourths, which is 13 pi fourths. Now I'm still thinking of a positive cosine, so I'm going to fill in the pattern for positive cosine, which would be max, equilibrium, min, equilibrium, max. Then I'm going to fill in the numbers. So my equilibrium is at 1. And since my amplitude is 2, my maximum will go 2 spaces up from 1, which is 3. And my minimum will go 2 spaces down from 1, which is -1. So everything we've done thus far is 100% the skills and the techniques, the method we would use to graph cosine. And then you would just go ahead and graph it now, right? Actually physically make your chart here. So we'll go ahead and make a trig chart. I just need positive x's and a decent amount of positive y's as well. So I'll do something slightly above here. And I'm just going to be approximating. Let's call that pi fourths, 5 pi fourths, 9 pi fourths, 13 pi fourths. That's about 13. and then 17 pi fourths. 1 is a good number, 2, 3 is a good number, and negative 1 is a good number. I like to draw my equilibrium line and plot the points. So it starts off at max, equilibrium, min, equilibrium, max. So everything up to here is 100% graphing cosine, but we're not going to connect the dots because I am not graphing cosine, I'm graphing secant. Now this is the idea. Any place that's on the equilibrium line, when you take the reciprocal, will be vertical asymptotes. So that's why I draw the equilibrium line, so I can easily see the vertical asymptotes, because these guys here, they behave as zeros. So when you flip them, they become vertical asymptotes. Maxes and mins will share common points, so I know these guys will be common points. And remember, the shape is always like these U's, these parabolas. They're not really parabolas, but I'm going to call them that. They're the U-shaped pictures that go away from the equilibrium line. And you're always graphing from left to right. So from this point here, I'm going to graph to the right, always graphing to the right, always graphing to the right. Some people like to complete the U's on the top and do this. I'm going to ask you to refrain from doing that. Since I don't have the X values labeled, we don't know exactly how narrow to make them. And I just don't want you to do the extra work. So please just leave it like this. And I'm going to be picky. If I asked you to graph a secant and you go ahead and give me these completed views here, I'm going to mark it off as wrong. Just give me the bare minimum 1 period. But that's it. There's the secant graph. You basically run through the motions of sines and cosines, except you just, well, you don't make the sine and cosine graph. You just make these arches here. For completeness of the notes, let's go ahead and do a cosecant graph. Suppose I ask you to sketch g of theta equals 3 cosecant of 3 times x minus pi thirds minus 1. Since it's cosecant, I'm going to think sine. So then list all the transformations. We have an equilibrium of negative 1, y equals negative 1. We have a right at pi thirds. We have a new period of 2 pi over 3, and there's nothing I can simplify there. And I have an amplitude of 3. Now let's do my viewing window. So I know that my interval is going to start at 0, 2 pi thirds. And I'm going to shift it to the right by pi thirds. So that means my new interval for my special x values, my critical x values, will be pi thirds, pi. So now I can make my xy table. 1, 2, 3, 4, 5. Starts at pi thirds, ends at pi, and then you just go ahead and make a bunch of averages. So then right in the middle would be 2 pi thirds. Here would be pi halves. Here would be 5 pi 6. Now again, I did this fairly quickly. I'm going to assume by now you're okay with figuring out these x values. If you're not okay with it by now, something is wrong. You need to start asking questions. And then of course the pattern. Well, our pattern is a positive sign. So the pattern for positive sign is equilibrium, max, equilibrium, min, equilibrium. Let's fill in the numbers. My equilibrium is at negative 1. My amplitude is 3, so the maximum, you go up 3 from negative 1, which is 2, and then the minimum would be negative 4. We go ahead and graph it as if we were graphing a sine. We're going to pretend it's sine here. So I got positive x values, but pretty negative y values with some positive y values as well, but more negative. So let's call this pi thirds. I don't know, approximating. Pi halves, 2 pi thirds, 5 pi 6, pi. And then I have 2 is a special number, negative 1 is a special number, and a negative 4 is a special number. My equilibrium is at negative 1. And the pattern goes equilibrium, max, equilibrium, min, equilibrium. And again, we do not connect the dots because that would be graphing sine. I'm not graphing sine, I'm graphing cosecant. So the idea is any equilibrium points become vertical asymptotes. The max and mins are shared, and you always draw U shapes away from the equilibrium line. So I know it's going to look something like that. So that is one period of the cosecant function. So that's it. That's the big mystery. That's how you graph secants and cosecants. You just go ahead and graph the basic sine and cosine, short of drawing the wave-like pattern, and instead you have to draw these special characteristics. Examples I did not show is, when there is a negative, but you remember, if there is a negative secant or negative or cosecant, just go ahead and do the pattern for negative sine and negative cosine, and then draw it appropriately. So all that will happen is these U arches will flip upside down. I'll leave that as an exercise for you. If you do have trouble, if you do want to see those, please, please, please ask questions.